Welcome to Abacus Tutorials. We'll be discussing the wing composite design using the software. In part 1, we described the theory. Part 2, we described the description to the problem. Part 3, we created a CAD model. And now Lifu Wang walks us through the finite element modeling using Abacus. Thank you, Lifu. Let's take it over and show how to do this.
Thank you, Professor Goyao, and hi everyone. Welcome to another finite element method tutorial. So to apply analysis, go to property first. So we create a property. The one layer property should be 2510 woolen fiber. CFRP. So, in the mechanical, choose elasticity, and then in the type, we choose the laminar. And enter the properties here, 55 gigapascal, so 55E9, 55E9. New one, 2 is given by 0.04. G12 is given by 4.3, E9. G13 and G23 should be the same because the out of plane direction is 3. And the constant we assume is E19. Sorry, 1E9. And then make sure everything is correct. Your name cannot start by a number. So let's call it Woolen CFRP. They have a 2510. Now, instead of creating sections, we directly use this one, Composite Layout Managers. So the problem is there should be 3 types of composites. The first one is generally about all the shell. It should be in a layout of this one. And for stiffness, stiffening shell, ribs and spars, issue in the layout of this one. But because there's an orientation problem, so actually we need a individual one for the sparse. I'll talk about this later, but let's create 3 of them. So create the first one, let's call it airflow shell. So initial apply for our first try, let's do n equals to 1, which is definitely not enough. That means your structure is going to fail. So later you're going to increase this number. So for first trial, we can input 5 of them. Sorry, 5. So to assign the region, first thing we need to do is to assign the region. To assign the region, let's do this. Let's just save this one. Sorry, it cannot be saved. So yeah, let's do it in this way. So click this region and then right click and select the added region. And we're going to include everything from before 0.1 and after 0.7. So before 0.1, hold shift and select this one. These are before 0.1 and also the bottom one. These 4 should be the airflow ridge. And then we select everything after 0.7. So 3 of them, because each interval is 0.1 of that. So 3 of that. Hold shift to select all of that. And if your geometry has some problem, you can hold control. For example, you select the wrong one, you can hold control and deselect that. That's a little bit hard to select, but should be this. and click the done. Now we're going to assign the orientation. Oh, before that, we assign the material property first. So click the material, right-click, edit material, select the CFRP we just have. Thickness, add the thickness. The thickness is 0.00 or 2.1 millimeter. So 0.21 millimeter, E-3. And then make sure that there are 4 zeros in front of 2. 1, 2, 3, 4. And then the rotation angle. Let's assign rotation angle first. The rotation angle is the ply sequence you have. So it should be 0, 30, 90, minus 30, and 0. So 0, 30, 90, minus 30. Notice that this rotation angle is in degrees, it's not in radians. And we click this one to make the calculation section symmetric. Remember that there are 3 integration points for each layer. So in total, we have 15 multiplied by 2, so 30 integration points. And this, then right-click this one, and then, well, we can leave it this now. So here, the definition for that, let's choose the part global. And then if you go deep into one of the coordinate system, you can see the reference coordinate system is automatically pointing to the x direction. That means you can see the blue angle, a blue arrow is pointing to the right. But we want the 0 degrees to be in the vertical direction, which is minus z direction or positive z direction. It doesn't really matter. So what we need to do is we need to choose normal direction in a different way. So choose the normal direction in axis 2, and it will give you z direction is pointing, like all the arrows, reference direction is pointing to the positive z direction. And just save it. You can see the parts we assign material become green. Now let's select, again, let's select this one. This step is just to make your life easier. It's not necessary. You can even do this before the previous step so that it will be easier. So after you select all of that, click this one, the remove selection. Now whatever left is the material that you haven't assigned any properties to. So create, call it stiffening shell. Is there stiffening shell? Yeah, stiffening shell. Use an underscore between them. It's safer. So for stiffening shell and also ribs, you should have initial plight of 4 plies. So choose 4 here. And then here, assign the regions. Sorry. So select all of that, but hold Control and deselect the ribs. Or let's doing this way. So we can select all the ribs, hold Shift and select all the ribs. Sorry, not ribs, sparse. And or this way. You can use the XZ axis here, and then hold Shift to select all the surfaces here. And also here. This might be easier. And hide it. And now we assign properties for ribs first, for sparse first. So move it to the side view and then hold Shift to and do the remove. Now you only have all the sparse. Create, call it sparse, and sparse has the same as the stiffening ribs. So call it sparse 4-layer, and then edit region, select all of that. Material, select this one, and then thickness 0.21 E-3, and then rotation angle, it should be 0, 45, 45, and 45 and 90. Yeah. So you can see that originally the surface, if you see from left, you need to make sure that your surface normal is pointing to this direction. The reason we need to split the ribs and the surface, the face sheet, is if you select the face sheet, the normal will be pointing to the Z direction, sorry, to the Y direction. But Y direction is in plane, so it doesn't apply to the ribs. That's why we need this one. So click OK for that. And use this invert tool to get rid of all the sparse, leave only the shell. Now use XZ and then deselect, hold Shift and deselect everything that we don't need to assign material properties to. So the rest you can directly assign properties, call it stiffening shell. So again, 4 applies and then region, select all of that, and then material, right click, select the woven composite. Thickness should be 0.21 E-3. Rotation angle should be 0, 45, 90. Yeah. And then look at the reference. Go to XZ view. Look at the reference direction. The reference direction is also pointing to the right. We want it to pointing to the positive Z direction. Choose axis 2 here. And then Once it's done, well, make sure that everything is green now. That means you have everything. Everything has assigned the material property. So now choose this replace all. So you have the geometry with the material assigned. Also double check. I think probably I forgot this. Yeah, I forgot to make it symmetric. Don't forget to include this, check this box, because our geometry is always symmetric, which means here, although it says 5, it actually has 10 plies. Here should have 8 plies, and here you should have 8 plies too. Now in the assembling, we create this assembling, choose independent. And in the step, we create a step analysis and choose static general. Just leave everything default. In the output displacement field output edit. Here, we don't need that many outputs. What we only need is, first, we need a stress for your problem. Also, we definitely need a strain. And we need displacements. And force, we enter the pressure force. So, well, here in the string, we need to choose specify, because we are going to output the layer by layer model. So we need to choose an integration point. Remember previously for each ply, we have 3 integration points, right? So from the top to bottom, we have the mid-plane integration point as 2, and then the next one should be 2 plus 3, 5, and then the next one should be 5 plus 3, 8, 11, and then 14, 17, 20, 23, 26. So you can consider your ply as 3 point is interpolating each ply. So in total, we have 10 plies for the composites. And we only output the results from the middle of the plies, which is integration point 2, 5, 8, and so on. And we should have 10 of that. 1, 2, 3, 4, 5, 6, 7, 8, 9, and then we need one more, 10. So I will show you like how do we use these results for. Now let's go to the directly go to the load. So the loading condition is pretty simple. So we first create at the initials, we create a fixed. So choose the symmetric, choose the base, and choose the enhanced encapsulated boundary condition. This is the fixed boundary condition. And then apply the load. So create lifting force or lifting pressure. It should be a pressure, and we apply the pressure at all the bottom surface. Hold shift to select all of that. Or yeah, you have to select that one by one. Don't select the wrong surface. So click down. And we're going to apply load at the brown surface. And the magnitude for that is after 1.5 of the factor of safety, we should apply the load at 33.6 E3. Should have this lifting force here. Make sure that everything is decent. Now we go to the mesh parts. So for mesh parts is one of the difficult parts one of the difficult challenges we have. So choose the XZ plane or this direction probably. Move it to the side direction. So we are going to have the same number of nodes for different sections. But notice that the length is different, so we cannot directly apply a global length and do it. So here we see the edge only. So choose all the edge. Hold shift to select all the edge. Like all the longitudinal edge. And instead of by size, we use by numbers. You can enter a default decent number. For example, 25 probably is 25 might be too much. Let's do 20. It depends on whether you have enough space to run the model or not. Because it's a shell element, it's relatively fast compared to the other method. And then now we are going to assign the node for all the cross section. So to do it, use by edge angle here. And then select this. This is a cross section we have. This is one of the cross section we have. Hold shift and then hold shift to select all of that, all of the cross sections. Here we're going to also use by number, but put a relatively larger 20 may be too large. 8 is already very fine because it means in this small region you have 8 of that. So probably 6 is enough. Yeah, let's do 6. So finally, we are going to assign the vertical one. So we only assign node at vertical line at the front and back. In the middle, it will follow the same logic. So hold shift, select all the vertical lines you have. And instead of 6, we can do 5 here. Now to begin with mesh, use the mesh control, select all of that, choose by individual, select all of that, and use the sweep. So there are some of them that cannot be swept. It will automatically change to free. So if you do it, you can see that. Let me show you more clearly. So you can see that this part of the spar and this part of the spar cannot be meshed using sweep because they are kind of like a triangular form. It cannot be meshed squarely. And okay, so let's see. Make sure your mesh is swept. And then the sweep path here, we choose a vertical one. Now the sweep is sweeping this direction, but we don't want it. We want it to switch this direction. Or I think it's because the selection is not good. So we can do this way. So we only select the shell surface. And then, yeah, the shell surface should be swept in this direction. So you can see the angle is pointing longitudinally. So accept the highlights. And then for the middle, I think it will automatically assign to a good sweeping path. So we don't need to worry that too much. Now we can draw the mesh. When you draw the mesh, you should have something like this. It's nicely looked, equally separated, and there's no weird things happen. So to check we need to double check the ribs and also the spars to make sure that there's no weird things happening. So select all of that. We can select the face. And select all the face here and hide it. Inside the spar, you should see this two should be meshed relatively good. And this two may have some triangular form, but it doesn't matter that much. Double check all of that. It should look good. Now we also check the sparse. We also check the ribs. So deselect all the boundary code control and hide it. You can see from the side view, you can see the ribs. The ribs should be meshed perfectly. It should be square everywhere. So if everything is done, now we can submit that for analysis. And create a new job. Call it like 12. And submit that. You can see that we only have 12,000 elements. So this should not be a very large number. If it is too large for you, you can decrease the mesh size. And it should be relatively fast. This only takes like 30 minutes or, 30 seconds or something. Let's see the result. So here, long click this one and select the plot the contour on both shape, deformed and undeformed. And we can see the displacement. And this is the displacement. You can see that there's bubbles here. These bubbles are the buckling of the shell. That is because when you have a bending here, the upper surface is under compression. And because our layer is very thin, so it will have buckles for the surface. And you can see those locations without the buckles are all ribs. So the ribs is helping you with keeping the cross section. So another way to design it is to add more, not ribs, to add more spars in the elevator. So normally in elevator, you have like a 10, 11 spars, but here to simplify it, we just use 3 of them. And you can see it also have a bending from the original shape to the upper shape. Well, to make it look nicer, you can choose common and then free edge. Originally is at the bottom. The new one is at the top. And to check the So our goals here is to determine the strain for each layer in fiber direction and make sure that it is smaller than this value. So to do it, the way to do it is first in the display group, you can select, see we have sparse, stiffening shells, and airfolds. Let's do airfolds first. So airfolds and replace, then you only have, and here we can choose the undeformed shapes. And you only have airfolds here. And then in the plots, there are several plots that probably is necessary to see. First thing is in the tools query, if you select all of that and select the ply stack plots, select the ply stack plot and then select this one. And then you can see the plies for your composite. It should be 0 degree, 45 degree, 90 degrees, 0 degree, 30 degrees, 90 degree, minus 30 degree, 0 degree, and then symmetric. And this gives you the composite layout informations. It may be useful for your report. The other useful plot definitely is plot. Select the result and select the section points here. And in the category, you can select either envelope or bottom up. Let's say a bottom. So this gives you the information for each ply we indicate. So remember that in the output results, we output number 2, number 5, numbers 8. Those represent the informations for each plies. So this is number 2, which is your first ply. So choose E and then choose E11, which represent the string in the fiber direction. This is the string in the fiber direction. And choose different layer and apply. You can see the values here. Positive means tension stress. Negative means compressional strain. And right now the compressional strain is 0.1, which is way larger than this value. So which means we need to increase the thickness for the shell or increase this n number. And also, you can double check the local direction. So click this one. In the options, material orientations, you can change the density for this. Originally, it may be very large. For example, originally it may be something like this. It's very hard to see. And you can shrink the size to like 5 or something, probably 4. And what's more important is the density. Change it to a very low density or something in the middle. This is showing you the material orientation. Where's the E11? So this blue represents the axis 1. And you can see for different so for different plies, you can have different orientations. The blue representing the E11, the direction for the E11 here. It depends on your ply angle. So go back to this one. We can have a quick check of the value. So here is the maximum, I think is ply ply 2 has the maximum compressional stress, which is 1.247. So 0.1247, 1247. Do a quick calculation compared to the our allowable strain is 0.005. So divide by 0.005. So it's 24. And let's try adding 10 more plies, or 10 more, that means 10 times the ply thickness now, and see whether it can improve this one. And I will guess you probably need to increase to 20 layers or even 25 layers. So that's one of that. Let's see the other one. Use this tool, invert this plate. And in the display group, we select the stiffened shell. And so this only gives you stiffening and the ribs. And again, you can check the plies here. Because stiffening, we only have 4 plies. So there's no ply 5 here. You only have 4 plies. And it's also very large. Probably you need to add another 10 more. So let's try another model with 10 more plies and see how do we change a ply. So in the properties, in your composite layout manager, edit it. This is another way to make a symmetric ply. So uncheck this one, and then here in the pattern plies, select symmetric and then leave it default. And if you do this, it will directly give you a symmetric plies. Now you have ply 1, 2. So this is 10 plies, is the same as what we do previously. So now we need to pattern this, all of that for 10 times. So another way to do it is we can pattern all of that for 5 times, and then click the symmetric. It's the same. It's the same. So select all of that, and then here choose the n copies. Let's copy 4 of that. So in total, you should have 50 plies, and then plus symmetric, you should have in total 100 plies. So you should see ply number 50 here. Same things for this one. So select all of this, and then pattern plies symmetric first, and then select all of these. It's a little bit hard to select. And then use n plies. We do 4 more plies here. It should end at 40, and plus symmetric, it should have 80 plies. And same thing here. Do symmetric first, and then we can uncheck the symmetric first. Sometimes it will run. You will need some time if you check this box. But n plies, n copies 4, and then it should end at 40s, and then check the symmetric. So now the thickness is 10 times. That means n and m is, sorry, where is it? That means N and M is 10. Both of them are 10. Now we don't need to change anything. We can directly go to the, I think you need to remesh it, I guess. No. So we don't need to change anything. We just directly submit. This time because, sorry, I forgot to do one thing. But this time it may take longer since you have more results. The step I forgot is, remember that here, when we output field output, we only output these. These only counts for 10 plies. But if you want to get the maximum compressional thing, you need to get the last several points. So to do it, the last ply, since now we have 100 plies, so the last plies are 299, 296, keep decreasing by 3, 293, 290, and 287. And probably that's enough. And also we need something for the 80 plies. We also have the ribs in 80 plies. Those 80 plies you need 80 times 3 is 240. So 239, 236, 233, 230, and 227. Actually, up to 230. That's it. So we need to run this one again. So those section points corresponding to the very first 5 layer for the 100 layer composite, and the very last 5 layer of the 100 plies composite. From the bending theory, you know that the maximum compression and the maximum tension will happen at the surface. So that's why we choose the very first one, 5, and the very last 5. Okay, let's see the result now. Let's plot on deform and deform. So now you can see in general, you don't have those bubbles anymore. You don't have those, that means you don't have bucklings anymore. What you have is a pure bending, more like a pure bending. And definitely you can see the string inside by selecting E and then E1 here. This gives you the string. Now the string, in general, you can see the string is much smaller than previously, but still the maximum compressional stress is still larger than the allowable compressional stress here. But let's see ply by ply. That may be even worse. So display group, let's display the airfill first. So choose replace and you only have airfill. And we only plot the undeformed shape. So go to results, section points. Now you have a lot of things, but let's see ply 1. This is ply 1. It looks okay. This should be smaller than 5. Ply 2. This is almost, this is a little bit, this is, I think it's still okay, but what about ply 3? So this is a good guess. That means you can see the compressional stress for the first 5 plies is all smaller than the desirable value. Then let's see what about the tensional stress. So let's see the last 5 plies here. So to do that, we need to go to symmetric tables. So for symmetric table, the last 5 of that is first ply 5. I think is symmetric ply 5. Yep. So symmetric ply 5, this compressional stress looks okay, and symmetric ply 4, symmetric ply 3, symmetric ply 2, symmetric ply 1. So it seems like 100 layers is a good assumption for the airfield, shell. And then you can use this to check other things, for example, stiffening and sparse, to make sure that all of them did not exist the maximum allowable strain. That is usually how we create a simple airfield elevator model and apply a boundary analysis to it and check whether the geometry is or the geometry or the design is a good design or not. So hope that you have learned something from this video, and I'll hand it back to Professor Go Yao. Thank you, everyone.